Hello everyone, hope you're doing well and staying safe. Just wanted to run through the second fire protection systems PowerPoint today, which is fire extinguishing system. So let's hop right into it. We first start looking at our engine fire zones. Basically, the fire zones are divided up into classes based on the volume and smoothness of airflow through the engine compartment. So we have our Class A fire zones. Class A fire zones are defined as having large quantities of air flowing past regular arrangements of similarly shaped obstructions. So the power section of a reciprocating engine, where the air flows over our cylinders through our cooling fins, is defined as a Class A fire zone. A Class B fire zone is where we have large quantities of air flowing past aerodynamically clean obstructions. So heat exchanger ducts, exhaust manifold shrouds, cowlings, tight enclosures that are smooth, free of pockets, and adequately drained. So they have a good amount of airflow through them. Turbine engine surfaces sometimes fall into Class B fire zones if the engine surfaces are aerodynamically clean and all airframe structural formers are covered by a fireproof liner to produce a smooth enclosure. So we've got that smooth airflow coming through. A Class C fire zone is defined as having relatively small quantities of airflow going through the area. The compartment behind the firewall of a reciprocating engine is considered to be a Class C zone. So obviously the area behind the firewall on a recip is not going to get much airflow. And when you think about it, it's going to be harder to address a fire that crops up there, as well as dispatching an agent to extinguish it. Class D fire zones are defined as interior wing structures and wheel areas that have little to no airflow, right? If we look into inside wing structure, our wheel wells, we don't really have a whole lot of airflow though flowing through there typically. And a Class X fire zone is we have large volumes of air flowing through, but they're at non-uniform or irregular rates. And if you look through your 4313 1B, it gives you a couple examples of Class X fire zones. (13) says Class X zone, area of heavy airflow and of unusual construction, making uniform distribution of the extinguishing agent very difficult. Areas containing deep recessed spaces and pockets between large structural formers are of this type. 4313 also says tests indicate agent requirements to be double those of a Class A zone. So these Class X zones, they have a large amount of airflow, but it's irregular and non-uniform, and it's going to be hard to get our fire extinguishing agents to adequately cover those zones in order to put out a fire. Turbine engine fire zones. A fire zone in a turbine engine installation is any area in which an ignition source together with combustibles, combustible fluid line leakage, or combustible mixtures may exist. So when we're passing any kind of flammable fluid through a turbine engine zone, that is going to be a fire zone. The power section, combustor turbine and tailpipe sections, which contain lines and components carrying flammable fluids, the engine compressor and accessory section, and any complete power plant compartment in which no isolation is provided between the engine power section and the engine accessory section. Obviously, we're going to have flammable fluids passing through those areas. Any fuel burning heater or other combustion equipment installation described in part 25.859, and any auxiliary power compartment. Obviously, these are going to be areas where we are going to have fire concerns, and so we're going to have to take steps to protect them. Next, we go into the two types or classifications of fire extinguishing systems. These are going to be 1, conventional systems, and 2, HRD or high rate of discharge systems. And we'll talk soon about why they are called high rate of discharge. Hopefully you can kind of get an idea by the name. So In a conventional system, we are going to use carbon dioxide as our extinguishing agent. This is very common in older aircraft. The carbon dioxide is stored in a liquid form. These are one of the earliest types of fire extinguishing systems for transport aircraft and are still used in many older aircraft today. The carbon dioxide is stored in steel or stainless steel cylinders that are usually wrapped with steel wire to make them shatterproof. The CO2 is distributed through tubing from the containing cylinder valve to the control selector valve assembly in the cockpit where we're going to control it. From the control selector valve assembly, it is routed through tubing to perforated loops which encircle the engines. This is going to be a distinction from HRD systems, which use nozzles, as we're going to talk about soon. In the conventional CO2 systems, we're going to use tubing that is perforated. It has holes in it, and it distributes that CO2 over a larger area. And here we can take a look at your typical CO2 installation. We have a vent line. There in the cockpit, you can see the CO2 cylinder. Our distribution lines that carry the agent to our perforated loops in the engine section to distribute that agent. This is a FAA test question. How does carbon dioxide extinguish a flame? Contact with the air converts the liquid CO2 into a gas and snow. If you've ever fired a CO2 fire extinguisher, you know the snow we're talking about. That snow smothers the flame. That is how CO2 extinguishes the fire. It is different than the halogenated hydrocarbons that we're going to look at later in the HRD systems. HRD systems, again, high rate of discharge systems, use halogenated hydrocarbons as the fire extinguishing agent. Sometimes they will use nitrogen as a pressure booster to help distribute that agent. The agent is distributed through few large-sized nozzles. And the outlets or the nozzles are located in the fire zone to produce a high-velocity swirl effect for best agent distribution. We want to distribute that fire extinguishing agent throughout the entire area evenly. It's crucial to be able to extinguish a fire anywhere in that area. And on the HRD systems, discharge occurs in less than 1 or 2 seconds. Hence the name high rate of discharge system. It discharges very fast. Now, when we start to talk about these halogenated hydrocarbons, we're going to see they are designated by a 4-digit number. Okay? Those numbers represent as follows. The first digit is the number of carbon atoms. The second digit represents the number of fluorine atoms. The third digit represents the number of chlorine atoms. And the fourth digit is the number of bromine atoms in the compound. If there's a fifth digit, it's the number of iodine atoms in the compound. The most commonly used HRD system extinguishing agents are 1211 in portable extinguishers and 1301 in aircraft-based systems. Halons are a little different than CO2 in how they address the fire. Halons actually extinguish a fire by chemically interrupting the combustion chain reaction rather than by smothering it. So instead of smothering the flame like CO2, we are going to actually chemically interrupt the combustion process. So we'll look into Halon 1211 next. Bromochlorodifluoromethane. I love these long chemical terms. That is the chemical name for Halon 1211. It's a multi-purpose class A, B, and C rated fire agent, effective against flammable liquid fires. Due to its relatively high boiling point, which is 25 degrees Fahrenheit, -4 degrees Celsius, Halon 1211 discharges as an 85% liquefied stream offering long agent throw range. So Halon 1211 will be discharged as a long liquefied stream, the higher liquid content, the easier it's going to be to throw that extinguishing agent farther distances rather than it is if it was more of a gas makeup. Halon 1301 is bromotrifluoromethane. Halon 1301 is recognized as an agent having A, B, and C capability in total flooding systems where we have a total disbursement. However, Halon 1301 offers limited Class A capability when used in portable fire extinguishers. That's why we see more of the 1211 in the portable extinguishers, the 1301 in the aircraft's actual HRD systems. The problem with these halogenated hydrocarbons is that they have some ozone depletion potential, ODP. Okay? They're not good for the environment. Halon 1211 and 1301 haven't been produced since '94 under the Montreal Protocol Agreement, where basically these countries got together and said they were going to stop the production of these agents. The search continues for more efficient agents to be able to extinguish aircraft fires. We try to walk a line between efficiency, extinguishing the fires, and toxicity towards humans and the environment. For some reason, the better it extinguishes a flame, the more detrimental effect it will have to the environment and to personnel. As far as those halons that were not, the countries agreed not to produce them, all the remaining stockpiles of 1211 and 1301 have been set aside for aviation. So a lot of systems that have these agents can still get the extinguishing agent. They just do not create it anymore. We're just running off of old stockpiles. In an HRD system, the halons are stored in spherical shaped containers. This was a common job we would have to do. Pull these containers out and weigh them to check the volume. Sometimes send them out to be hydrostatically tested, recharged, and then reinstalled in the aircraft. So if you look at this HRD system container, we have our mounting tabs where we mount to the airframe, a pressure gauge to give us an idea of the internal pressure. We have a fusible safety plug in the case of overheating, and you can see we have a line venting to the red disc and the overboard vent. And we'll talk about this a little bit more later. Basically, if temperature of this HRD containing vessel gets high and the internal pressure becomes too great, we're going to break that fusible plug and we're going to vent this extinguishing agent overboard. We don't want the container to explode. There we've got our firing bonnet, which houses our squib, which is an explosive cartridge that when it detonates, it breaks a frangible disc in the container, which releases the agent. Here we can see an HRD bottle assembly in a 737. There you can see our pressure gauges, as well as all our plumbing to connect the agent bottles to their nozzles in various locations in the aircraft. So what holds the halon in the bottle? What keeps that agent in the bottle? That is the frangible disc and or a fusible plug that is used like a thermal fuse. The fusible plug is a safety device which breaks when the bottle itself is subjected to high temperatures, which in turn overpressurizes the bottle. If you think about it, if we overheat this container enough, its pressure is going to rise to the point where it's going to be essentially a bomb. We want to allow a way for that agent to be automatically released from the containing vessel and vented overboard to prevent any catastrophic explosions. Makes sense, hopefully. In the case that we want to manually discharge, right, we want to dispatch these agents to a fire, when we press the extinguish button for our fire protection system, it is going to send an electrical signal to a squib, which is basically a small explosive device. It's going to break the frangible disc and allow that fire extinguishing agent to flow to where it's needed. There are two types of squibs that we talk about. The slug type. This type actually fires a metal slug through the frangible disc into the container where it's contained, which allows the agent to flow out. We also have the shock wave type, this type is just basically an explosion. The shock wave of that explosion is enough to break that frangible disc, releasing the fire element. Here you can see the slug type in this slide. You can see how it releases that agent into our plumbing and out to our discharge nozzles. The service life of the squib cartridge is calculated from the original equipment manufacturer date stamped on the cartridge. Service life is usually in terms of hours below a temperature limit, or in years from installation and storage. This was another common job I would do, is remove these squibs and replace them if they required it. The total life of the squib starts on the day the cartridge is made, and you must replace it at a specific time. This includes any shelf time. So the total life, it starts from the date of manufacture and includes any shelf time. Service life is a little bit different. Some manufacturers require a reduced life starting from the date the cartridge is installed in the cylinder. So that's just the time that the cartridge is in service. The big thing about these that I want to get across, these squibs, is that you need to be very careful when disconnecting the electrical connections. If a static charge or a voltage is applied to the terminals on the squib, you can accidentally discharge the squib. I've seen it happen before. So what we're going to do is we're going to make sure before we remove these cartridges that the cartridge terminals have been properly grounded, shorted, or shielded to prevent accidental firing. Typically, the easiest way to do this is we're going to wrap a piece of safety wire between the two electrical terminals. That way we know those terminals are at the same potential. In other words, there is no voltage differential between them, which would cause that squib to discharge. When we do remove a squib from a bonnet assembly in an HRD bottle, we never use it in another bonnet assembly. Sometimes they can be specially sized to fit a certain container, and we don't want to risk a malfunction in our extinguishing system because we used an incorrect squib. Now we're going to talk about the yellow and the red discs on the side of many aircraft with HRD systems. Typically they're located on the outside of the fuselage. If you go to the Sabre liner, just aft of the left wing, you will see a yellow and a red disc. What are the purposes of these discs? Well, the red disc, if it is missing, it means that the HRD bottles experienced an overpressurization situation, usually caused by excessive heat, and that thermal fuse has broken, and it will release the contents of our HRD bottles overboard. Right? So this was an overheat situation. Pretty easy to remember. Red, we had an overheat, aka overpressure situation. The bottle automatically discharged itself. When the bottle becomes overheated, the pressure built up by the heated fire extinguishing agent breaks the fusible plug on the bottle. The agent is then routed through tubes and lines where it contacts and breaks the red disc. Basically, it breaks the red disc on its way overboard. This agent is dumped overboard, it's gone. Here we can see how that kind of works. Here's that red disc. There, that pressure comes out of the bottle, shatters the red disc, and that agent is exits overboard. The yellow disc indicates that the fire extinguishing bottles were discharged by a manual action, which means that the flight crew discharged the bottles. This means the agent is sent through the normal discharge nozzles to put out a fire as detected by the flight crew. Here we can see how that yellow disc often works. Here we have a spring and a plunger. When we discharge that extinguishing agent, we don't want to vent any overboard, so we're going to use this plunger and spring assembly to push that yellow frangible disc out and break it without releasing our agent into the atmosphere. We need that agent to go into the nozzles and address our fire situation at that point. So if the red disc is missing, we had an overpressurization event with our fire extinguishing agent. If the yellow disc is missing, we had a manual release of the agent by the crew. Typically, each engine will have 2 shots, right? We want to have 2 tries to get that fire out. Most CO2 system containers and some HRD system containers do not have any means for visual inspection of the amount of extinguishing agent in the container. In order to do this, they have to be weighed. This was another common job. I'd pull fire bottles out, weigh them to determine the container charge. Again, many of them also had to go out and be hydrostatically tested. DOT actually regulates the hydrostatic testing on these vessels, and typically they're good for a 5-year period before they have to be re-hydrostatically tested. Fire extinguishing containers must carry marking which show the month and year of their last hydrostatic test. RIN is a hydro test date code assigned by the DOT to uniquely identify the qualification date and the facility. So here you see a couple examples. 6, then we have an A over a 106. So the date here is 6 June of 06. And there on the right you see 1007, October 2007 would be that requalification date. Pressure checks on HRD systems. Most HRD systems have a pressure gauge mounted on the bottle itself. Periodic pressure checks are made using a pressure temperature graph. So you'll have a graph in the manual that gives you the ideal bottle pressure at a given temperature. So you're going to have to know the temperature of the environment in order to determine whether that pressure reading is acceptable or not for that bottle. I spoke before a little bit about the ozone depletion potential of these halogenated hydrocarbons and the problems those cause. The Montreal Protocol was signed in 1987 and called for a total ban on the production of many halogenated compounds, including halons, in 94. So they agreed that they would stop producing these, but the existing stockpiles have been reserved for the military and aviation, so there is still some access to that. And we also have an exemption. Basically, it lays out that certificated aircraft manufacturers and owners could still have access to 1301 in order to meet the requirements of their fire suppression equipment, because no agents that could meet those requirements had been found at that point. There is a new agent that has become pretty popular, pretty exciting as far as fire protection systems go, Foster X. and it debuted aboard the Eclipse 500 jet. These systems are really small, amazingly small. Foster X is the only non-halon engine fire suppression system approved by the EPA and the FAA both. The result of these dual approvals is that Foster X is the only fire suppression system today that can meet the standards of the Montreal Protocol. Until now, aircraft were exempt from the treaty and allowed to use halon until a sustainable replacement was available. Foster X seems to be that agent. Foster X is more potent than 1301. 2 teaspoons of Foster X agent are equivalent to 2.5 cups of halon 1301. The vessels holding the Foster X are incredibly small. I'll throw up a picture here. In the Eclipse 500, the total weight of the Foster X fuel suppression system is about 90% less than a traditional halon system. You can see any kind of weight savings like that is really going to appeal to the aviation industry. So here is our Foster X containing vessel. You can see the pressure gauge at the top. We have a cannon plug for an electrical connection, and we have our, is that an AN or an AC fitting? How would I tell? You can see it though against the dime. These bottles are tiny, and here is a Foster X container compared to a 1301 container. The Foster X high fire suppression system is less complex than the halon system. It's designed to be maintenance free for 10 years. After 10 years, all we're going to do is swap in a new Foster X container and continue on with our lives. This eliminates the typical hydrostatic and visual 5-year inspection associated with the halon systems. So this has been really a exciting development in fire suppression for aircraft. And you can go online, here are a couple links. You can go online and read more about that. So that is basically it for the fire extinguishing PowerPoint. Make sure you go through the PowerPoint yourself. If you have questions, let me know, and I will do my best to answer those. Hopefully you are doing good. Stay safe. Talk to you later.